I am Patrick de Causmaeker. I'm a professor at the University of Leuven. Lennart, originally in 2021, came to me as a master's student. And I kind of attracted him with the title. And you can guess which words in the title were important for attracting him. The title was Computing the 9th Dedekind number using supercomputing. So which is the word that attracted him, you think? It was, of course, supercomputing that attracted him, but he really got involved into the first word, the first problem, namely computing this Dedekind number and the intrinsic mathematics and computer science tricks, algorithmic inventions that were needed to realize this project. I mean, he got stuck in it, and it didn't release him until beginning of April, but even now, I must say. So what we will do is I'll give you a very brief introduction into what this Dedekind number is about and what is the history of it. That will set a little bit the framework in which this project has happened, and then we'll hand over to Leonard to tell you what he really did to be able to compute this 9th Dedekind number. We have been together for 3 years since then, Leonard, of course, and Jens Humare, who is here as well, talking over the internet every week. I think once a week we had a meeting. So it all starts in 1897 when this famous mathematician, of course, Richard Dedekind, in German, wrote this paper on Zerlegungen von Zahlen durch ihre größten gemeinsamen Teile. Most of the presentations that I've been doing on this subject until now, I had to translate this title, but I think I don't need to do that here. So he was interested, and this is really important work. So this paper is an important paper for the structure of these numbers. He realized that it is actually a partially ordered structure, and he described it in detail. And it was the start of a lot of ideas and inventions in mathematics. But at the end of the paper, he wrote this paragraph, and he says the number of elements in this group. He was talking about a group that has to do with those. How many elements are there in there? I tried to compute them, he says, and it is 18 if in the case n equals 3. I'll come back to the meaning of n in a minute when I describe you the problem itself. But for n equals 3, so that's the third Dedekind number, it is 18. And wenn ich mich nicht irre, it is 166 in the case n equals 4. Now, for people who have looked at these numbers, this series, they may remember the first 3, and they will notice that 18 is actually 20 today, and 166 is 168 today. So, wenn ich mich nicht irre, well, he was not wrong. Of course, he was not wrong. But his definition was a bit different from what we use today. And I'll explain what the two extra elements are actually in those sets. So this is, and as you see, wenn ich nicht irre, he needed already some effort to compute this 166. It's not hard, but it's certainly not trivial either. He didn't move any further, but it took until 1940 when Randolph Church, who was also interested in aspects of computer science, in 1940 he came up with the fifth Dedekind number. So this is the definition of the problem according to Randolph Church, and this is the method he used. He used the tabulation method. So as far as I know, I didn't find it. I don't think he does refer to a computer at that time. So I think he did it by hand, actually. And he found the fifth Dedekind number, number 5. And what he writes is, you cannot see it, but it's 7,579. And on the website of the Open Encyclopedia of Integer Sequences, it is mentioned that this is an error. Well, of course, it's not an error. And he's using the definition of Richard Dedekind, because today we know that, well, we know the number as 7,581. All right. So here is 166, and there is 18, and here is 4, which Dedekind didn't even bother to mention. So that's the Richard Church, who takes on this problem. And a little bit later, in 1946, and I'm sure a computer was used in this case, there was this note on the free distributive lattice, which is becoming the terminology that we know today. And he says, I've done the 6th one. This is the number. This is the result for the 6th one. And again, if you look at the tables, you will see that the last digit is not correct. It's a 4. It is not a 2. And he refers to the result of Randolph Church. And this is 1946, the 6th Dedekind number. We jump to 1965, and for some reason it is not on this slide. I was looking for it, but I don't know. I didn't find it. 1965. Randolph Church computes the 7th number. So he's got the result for the 7th number, and it is correct. I think it is already in the new definition at that time. But it takes until 76 until somebody else is able to redo the computations, and it happens. And they are correct. 1991, Doug Wiedemann computes the 8th number, and he's using this formula. I've shown you the tables of Church. I've said that Ward was using a computer. I've not explicitly shown you a formula. I think this is an interesting formula, which was, I think it was found a little bit earlier, but okay. So this is some advance which allows Wiedemann, together with the computer architecture of the 90s, which was actually a kind of a test for this architecture at the time. He succeeds to compute the 8th number, and now it is correct. So 8 is the last digit of the 8th number of Dedekind that Doug Wiedemann computed in 1991. He compares it with a formula which was developed in the meantime, Korsanov's formula, which is an asymptotic result, and gives you an idea of whether your value is at least exact, is at least nearly exact, let's say. But okay, so those are the digits, and that is what we are talking about. The gamma here is a permutation factor. So he is using symmetry as well. He is using symmetry, so he's summing over R6 and D6. And D6 is a full space, while R6 is the space of non-symmetric elements in this structure that we are counting. And I didn't tell you anything about the theory until now, so you cannot understand it. But okay, so this is a formula. And then, of course, in 2023, Lennart Van Hirtum came up with this result. Please.
So all these results so far are not, like they're claiming this is the correct answer. It's not like a heuristic which suggests, okay, here's a guess as to what the number is, and then it has to be verified. They claim it's the exact value, and of course somebody needs to check it. Sometimes it takes 10 years, fine, but it's an exact computation.
It is an exact computation, yeah. It's not a heuristic guess. Korsanov's formula is kind of, is an approximation. So it gives bounds, but... sorry?
There was an asymptotic formula you mentioned.
Yeah, this is Korsanov's formula, among others. That one is not exact, no. and we were contacted by another colleague who is working on a probabilistic computation of the Dedekind numbers, which is much sharper than Korsanov's formula, and he could check the first how many digits.
It was accurate until about 10 digits.
10 digits. 10 of the 42 digits were correct in his formula. It is also not guessing. It is a probabilistic way of computing. But okay, this is not what I'm talking about. But so this kind of things are happening. But again, here, this is a counting problem. So we're always counting. And when I say this formula, this is an exact formula. So this is the exact number of permutations of R. So these etas, I'll define them in a minute. So those are exact values, which stem from the algebra of this problem. Okay, so it's time to tell you about the problem, I think, and I've drawn just an example of a partially ordered set. So the red arrows, the blue elements, the blue bullets are the elements of my algebra, and the red arrows are the direct comparison. So the one directly larger than this one is this one. So there's nothing in between. Also here we have the same thing. Okay, so there are two elements directly smaller than that one. But of course it is an order relation, a partial order relation, so it is transitive. So this element is also smaller than that one. So we've got a transitive closure, but when we draw the diagram, we often only draw those red arrows, so direct comparison. All right. So the question of Dedekind is not about this example, but it can be translated in it. You can wonder if I assign Boolean values to my elements, and I do it in such a way that if I go up one step, that if I assign a value, I assign a Boolean value, a true or a false. So let us say that now everything is false. Here I have selected one element, so that one is true, and the other ones cannot be false. So this one and that one and that one, they are false in this diagram, but this guy must be true because I want my assignment to be monotonous. So it should respect the ordering. So if I go up from that one, anything that I find must be true. Yes? Must get the value true, and those are all false because I don't indicate anything. So I can do that like this. I can use something like that. Only the top one is assigned true, let's say, or I can use those two, and then what should be true is this one, and that one. In my drawing, those are false, and then I can do something like that. So those two are false. This one is true, and that one is true, and anything above those is also true. So you can see what becomes true if I set it this way. What I've used to illustrate the monotone Boolean function and the way I explained it, that is the framework Lennart has done his computations in. There is an alternative which is useful for some other purposes and can be used more in theory maybe, but also in computations. That is the idea of an anti-chain. If you look at my rectangles, none of the elements that are in a rectangle can be compared, because that is how I put them. That is how I described you my monotone Boolean function. Such a set of sets we call an anti-chain. All right. So the top of a Boolean function is an anti-chain, and the question of Dedekind is how many Boolean functions are there, or how many anti-chains are there. and I did the exercise. I hope he didn't hear. I hope I didn't make a mistake. I think the number on this diagram should be 50. So you can do the exercise if you want. And if I'm wrong, please come and tell me. This is closer to what Dedekind was talking about. What we have here in the bullets are sets of a number of elements. So this is the empty set. This is the singleton 1, the singleton 2, and the pair 1, 2. So a set with 2 elements, 1 element, and so on. So, and the red arrow describes the inclusion. So the empty set is a subset of the singleton 2, of course, and of course a subset of the pair 1, 2, but also a subset of the singleton 1. The singleton 1 is a subset of the pair 1, 2, and that's it. So the partial order we're talking about is inclusion of sets, and the elements are the subsets of a set of n elements, and n is the number we're talking about. So in the case of the 9th Dedekind number that we're talking about now, we're talking about 9 elements, subsets of a set of 9 elements. Those are the elements of my monotone Boolean system, and my ordering is simply inclusion. And the question is, if I define a monotone Boolean function on this structure, how many options do I have? How many such can I create? And what Dedekind said was, well, if you don't assign anything, that's not interesting. If you take everything, it's also not interesting. So those were the 2 elements he didn't count. That's hence his 166. Okay. You can do the exercise if you want. This should be 20. And okay. So this is the structure of the subsets of a set of 3 elements. I go back to the sets of 2 elements here, as you can see, but the ordering that I'm using here now and the elements that I am depicting are not the subsets of my set, but are actually the monotone Boolean functions. So this is, but I'll have to explain you a little bit how it works. If I think I have the time today. So the notation that I'm using is one that goes back to Dedekind. There was a referee at some point who was a little bit angry that I used this notation, but then I said Dedekind was already using it. So this 1, 2, for example, here, that is the set with 2 elements, 1 and 2. And when there is a 1, it stands for the set with 1 element, 1. I admit that it is a little bit confusing, but it makes the notation more concise. And Dedekind said, we're never going to make it up to 10 anyway, so why bother? I use the digits to indicate my sets. And I describe a monotone Boolean function on the sets as a set of such sets. So this is an empty chain in that algebra. Did I lose you at this point? I hope not. Yes, please.
A little bit. So before it seemed like you're counting the sets of empty chains, yeah, or the number of empty chains. Is that correct?
I was cutting the. Sorry.
You're counting, given a graph.
Yeah.
Labels on the nodes, right, with some partial order. You're counting the number of empty chains. Is that correct?
Yeah, anti-chains or monotone, which is equivalent. Yeah.
Yes.
Yeah.
But that seemed to be graph dependent, like depending on how you set. Like, do you see what I mean? Like you gave me an input graph, and depending on the dependencies,
yeah, sure, of course.
Right? So, but when you're counting monotone Boolean formulas,
Yeah.
presumably the graph structure is fixed.
Yeah.
Right.
Yeah. The graph structure of my monotone Boolean algebra is fixed. Yes. Yeah. Is it okay? Yeah. But of course, I mean, in my first example, you couldn't use this notation. It wouldn't make sense because it's just a partially ordered set. It's not nothing else. But in this case, it's nicer to use these. And what you see here are the anti-chains, and they represent monotone Boolean functions in the sense that anything that is below, that is a subset of one of or that has only elements which are subsets of the elements in this anti-chain are in the monotone, are recognized by the monotone Boolean function. Okay, so this is my my structure for the case n equals 2. Just to give you one example, one quite early and rather elementary example of theorems that have been proven in this context. If you complete the order and you allow reflexivity on this structure of antichains, or the structure of antichains, and then you count all the arrows, including the circles, of course, you end up with 20 in this case, which is the next Dedekind number. So the number so this is only an example, which is quite important actually in the computations. I think Ward was definitely relying on it already, so it is an old. But this kind of properties have been proven, but it goes further than that. Okay, we're talking about April 2023 now. If you look at publications and the mentioning of Lennart, he will also always mention the 8th of March 2023. But we were a little bit in doubt because there were some probabilities of errors which we didn't really manage to understand very well, which kind of made us uncertain whether the result obtained on the 8th of March was actually correct. But it was there. And then and we were working on a paper for a conference which Lennart will visit in a couple of months, and where this work would be presented. But we were kind of considering, yes, how do we want to publish it, because this uncertainty is there and so on. So we were not really very certain. And then on the 5th of April, I came across this name on the Open Encyclopedia of Integer Sequences. So on the website, we were working on that paper, and I was consulting that website, and I saw, okay, there is somebody claiming to have computed A9, the 9th Dedekind number. So, and it was actually the case. So Christian Jekyll at TU Dresden had published a result on arXiv and also sent it to the Open Encyclopedia on the 4th of April. So just one day before I noticed it was there, there was this result. So I started immediately communicating with the people, the editors managing this website. It took me a day, a night, and another part of a day without much sleep. But then in the end, we had our result also mentioned, because the result that Jekyll was announcing was exactly the same that Lennart had announced internally on the 8th of March. And I'm telling this story for several reasons. I mean, we wanted to be correct. We didn't want to publish a result on which we were not certain, we had doubt. So we wanted to document our doubt, and that took us some time, so we were busy doing that. But the other thing is, Christian Jekyll didn't know about our result, and our result was time-stamped on the 8th of March. So since those two results were exactly equal, we could be fairly sure that we were both correct. In any other situation, for example, if we had published it immediately and then 2 weeks later Jekyll came up with a result of his computation and said, I got the same, but since he didn't know, it was a blind race. So I think we can be quite sure that our number is correct. I've collected, just to show you some of the mathematics. He refers to this paper of Pieter Jan Hoed, who was a student of me at some time in 2016, if I remember well. So this formula is actually the same as the one that is on top of that is there. It makes a jump of 3, and Leonard will explain you what a jump is. But Jekyll went one step further, and he made a jump of 4. And he introduced this notation of this construction, this mathematical construction, which is very well suited to be used on the GPU architecture that he was computing on. And this is this is what we lived through in the beginning of April. And he says, Jekyll, at the end of his paper, the only thing left to say is that we run the algorithm on NVIDIA and so on. So many matrix multiplications. This is the number. And this was exactly the number that Leonard had come up with another method. Not only on another computer infrastructure, not only completely independent, but also with another method, because he is using this formula where this coefficient plays an important role. It resembles a little bit the formula that Wiedemann is using, but this factor here is not a symmetry. You can do symmetry, as you can see here, extensively. Yeah? Leonard worked on this formula, and he will tell you about it in a minute. But this coefficient is called the p-coefficient. It is the number of connected components of a graph. And it can be best formulated, and I realized that it was the case by looking through the glasses of the anti-chains. If you look at it from the monotone function perspective, it's much harder to see, but the alpha and beta are anti-chains, and the elements of, I think, of beta are the vertices of my graph, and the arcs are intersections of sets which are not below alpha. So that defines a graph between the 2 to the 9th vertices of an anti-chain beta. And the question is, how many connected components does this one have? This was a central challenge for the master thesis to devise a computational system that was very fast, and that is what Leonard definitely realized, and that's why this formula worked so well. So, as a simple table, this is where we are. It goes up, as you can see. Double exponential. One of the questions I have, why did it happen that approximately every 30 years over the last century, a new Dedekind number was found? If it is double exponential, it cannot only be explained by the growth in the strength of the hardware. Could be that the programming techniques on that hardware evolved, but I think the mathematics also plays a role, and we'd like to have a deeper look at this. This is where we are, independently computed by Lennart Van Hirtum and so on, and the people, of course, from the Parallel Computing Center of Paderborn, which I think was a great venue to come to. This was an opportunity for you, Leonard, to come here and to do this computation and to get involved in this research. I think the word is yours now.
Whew. Hello, here we are. This presentation has been a long time coming, even before I came to Paderborn. So, like Patrick said, this project originally started as my master's thesis about 3 years ago. And right at the end of the master's thesis, as I got the vibe that computing this thing would work really well on FPGAs, I reached out to the kind people here at PC², specifically Christian. I found his name on a random slide somewhere on Google. And so this is how we came in contact. and we've been working together then for the last 2 years to make it a reality. And finally, about 3 months ago now, I actually started working here at Paderborn University as a PhD student. So I will be presenting to you this project of the last 3 years of my life today. So again, here you have the list of all of the Dedekind numbers that are known up to today. So as Patrick showed you, the dates, they start in the end of the 19th century and they go all the way up to 2023, when within the span of 2 days, 2 publications suddenly came out, both claiming computation, first computation even, of the 9th Dedekind number down here. It's a massive number, like it's huge, like Trump would say. And the thing is, these numbers, they follow a double exponential, so these grow at the rate of 2 to the power of 2 to the power of n. This is a very, very small and innocent-looking formula, but if you just fill in n is 9, you already get 2 to the power of 512, which is already a humongous number. Sadly, computing these numbers follows a similar trajectory. So the complexity of computation is around 2 to the power of 2 to the power of n minus 1. So we can get the minus 1 there, but that's about it. Is there anything else? No, I think that is it. So, oh yeah, also, just to illustrate, using my current method on CPU computing this 9th one would take several hundred years. But using the same method for the 8th one takes 8 minutes. Using the same one for the 7th one takes several milliseconds. So just this is the enormous scale that we're working here. It's innocent, explodes. And so the 10th one, I'm claiming it won't ever be computed, and I can do that, so I can be proven wrong. Or I'll be dead by then. So I win either way. So I'm more of a visual person, so I will give you more of the visual view, how I see these monotone Boolean functions. So these Boolean functions, everybody knows what they kind of look like. They're a truth table. So you've got a function, takes in a number of inputs, and it just has a big table that says, if everything is 0, we output 0. If everything is, like A, B, C are 0 and D is 1, then we output a 1. Like we have a truth table for every possible input combination. So that truth table is down here. And what we'll do is we will apply a certain constraint on this. This constraint is what Patrick also alluded to. And visually, it is very simple. If we represent our Boolean function as a graph like this one, where like the contents of the nodes say which of the inputs is 1 for your Boolean function, we structure them like this, then the rule is a white node may not sit above a red node. That's the only rule. And so counting these Boolean functions is then counting how many of these Boolean functions, like the number of Boolean functions is pretty trivial, it's just 2 to the power of 2 to the power of n. How many of these do satisfy this property? Also, interestingly enough, these structures are actually hypercubes. So if you're working in 3 dimensions, you'll get a cube. If you're working in 2 dimensions, you'll get a square. And if you're working in 9 dimensions, you get a very, very impressive poster. On the right here, we have a different representation of our Boolean function. This is the hypergraph representation. So in this case, what we do is we make every input or every name of our Boolean function a node, and we just draw a line between them if the corresponding node or if the combination of them would return true. So like, for example, this BC node here corresponds to this BC edge here. And so the higher nodes, ABC here, corresponds to this 3-dimensional or degree 3 edge in the hypergraph. These nodes here, they correspond to like the edges from a node to itself, I haven't really drawn them here, but you can imagine them. And then this one is an edge that is between no nodes, and I guess you can't imagine that one. And of course, if we have all nodes, that would be a 4D hyperedge, and that would correspond to this one. So this, yes?
Sorry, something minor I'm missing. So in the first half of the talk, if it was monotone, so if CD was red, then ACD also. If CD was true, then ACD also had to be true, right? So, but you said something completely opposite to that now, right?
So the fundamental structure remains the same. So it does not matter if we make the values on top true or on the bottom true, or if we color them red below or purple above. So it's the convention varies like regarding to what is the most convenient at the time, but you're always talking about the same structure.
But the partial order itself is defined the same way.
It's yeah, the same way. Right, so this picture here on the right is mostly useful for something called canonization, but we'll get to that. The translation of this monotonicity requirement to this hypergraph notation is also very nice, because the rule is you can only draw an n-dimensional hyperedge between n nodes if all n-1 dimensional hyperedges between them are all present already. So for example, we could not draw this 3-dimensional edge if these 3 edges did not already exist. So here is then the monotone Boolean function structure for the first 3 Dedekind numbers. So here is the 0th, 1st, 2nd, and 3rd. And you can recognize these Dedekind numbers. So there are, for example, 6 possible monotone Boolean functions for 2 dimensions. There are 20 possible for 3 dimensions. And so this is also where you can kind of see this plus or minus 2 confusion, because these here, they're kind of special. And so originally Richard Dedekind and the researchers that followed him did not count these. We do. It's just a matter of convention. Does everyone understand this picture? Excellent. And so for the later, like for the bigger graphs, they always get twice as high, but they get exponentially wide. There are lots of possibilities, like in, for example, 7 dimensions with exactly 53 nodes, you will already have millions of possibilities. So the core idea we use for computing these Dedekind numbers efficiently is what we call jumping formulas. And I'll give you a very simple introduction to the most basic jumping formula we have, the one jump. So this is the formula. Doesn't look too scary, I think. We do have the big summation symbol, but it's not too bad. So what we do here is we sum over all monotone Boolean functions of dimension n. So that is what this here means. This is the set of all monotone Boolean functions of dimension n. And we add up their interval sizes from bottom. Now, what does this mean? Well, I'll first explain it visually. So let's say this red one here on the side is our alpha. Then the interval size to bottom would mean all monotone Boolean functions which we can stick next to it, such that like we extend our hypercube in the next dimension, such that our monotonicity requirement is still valid. So again, in this case, none of these extensions violate the rule that we have a white node under a color node. And so for this specific one, we have 5 possibilities. We have the empty one, the one with 1, the one with 2, and 2 that way, and the one with 3 nodes like that. And you can actually see it, these interval sizes in this structure, which is why it's so nice. You can start at a Boolean function here, and these are just all of the Boolean functions in the interval below it. And so you can start like at this one, and then count them all down as well. So we have this one jump formula, but if we have to compute each of these intervals, then we're not really gaining anything, are we? Because we still have to iterate all of these Boolean functions below them, so we're just iterating all MBFs anyway, just in a funky way. Well, we can already do slightly better by removing the symmetries. So that is, Patrick also alluded to it before, and that is what we do here. So instead of iterating over all Boolean functions, some of these Boolean functions will look very, very similar. Like, I'll quickly demonstrate that here. Look on the left here. This A Boolean function and this B Boolean function, they have actually the same structure, like they're kind of rotations of each other, or like swaps of the variables. Like, and we don't really particularly care about the naming of the variables. So actually, we could just treat these two as one Boolean function. And so we can just group them in one thing we call an equivalence class. So this is an equivalence class which has size 2. In 3 dimensions, it goes even further. So here we can draw each of these equivalence classes. And you will notice these are kind of rotations of our hypercube. Now, we can't just select the full layer, because the structure of these 3 little ones is similar, like they're kind of the face, one face of the cube every time. But this one in the middle here is not, it's kind of the top corner of the cube that is colored in red this time. And so we do have to separate these out. These don't have the same properties, but these that are in the same equivalence class, these do have the same properties, and we can use that. Now, how do we group these Boolean functions to make sure that we do have all of the equivalence classes for our work? Or, like, say you store the information for everything in a certain equivalence class. How do you figure out, how do you, like, map onto an equivalence class? That is what the canonization operator is for. So canonization basically means you can start from any naming of the vertices and do a certain set of operations, like swapping them in a certain deterministic way, such that for any permutation of these input vertices, we end up at the exact same output permutation. And what we can do then is we just call this one our representative, we hash it, and we can use this in our lookup map. But, of course, nothing is for free. If we want to do this, like a naive way of doing this canonization, would just be do all variable permutations and just define an arbitrary total order over them. Like the one I use is just do integer comparison. Like you have a binary representation of your graph, just integer compare it, and you will have one element which becomes the minimum, and we just pick that one as our canonical version. But the problem is, we have to do all n factorial permutations for this. And we want to do it faster. So one technique I developed in my master's thesis was this thing called vertex distinguishing, where ahead of time, we try and assign some names already, or try and collapse some of these permutation groups already, so we have to do less work. So for example, any way this vertex would be named, we can see it is the only vertex with exactly one 2D edge coming into it. So we can already give it a deterministic name. Likewise, this one here is the only one which has exactly one edge coming into itself, a 3D edge and a 2D edge. No other nodes are like that, so we can give it a deterministic name as well. But these two at the top here, if we count the edges, we cannot distinguish them yet, because they all have two 2D edges coming in and one 3D edge. So for these cases, we still have to go through all remaining permutations, but instead of 24 permutations, 4 factorial, we only need to do 2 permutations. And we cut down the total amount of work by a lot this way. Here you see a list of all of the equivalence class counts. So for every dimension of your Boolean function, it shows you the number of equivalence classes. So these are highly correlated with the Dedekind numbers. They also follow the 2 to the power of 2 to the power of n formula. And you can see here this 5. So in the example for the Dedekind structure for 2 dimensions, we had 6 nodes, but remember, 2 of them, A and B, we could merge them together in one equivalence class. So we only have 5 distinct equivalence classes. And again, for all of the bigger ones, it again explodes to very, very large numbers. Interestingly, in the last 2 years, this has actually advanced quite a lot. So when I started my master's thesis, these were not known yet. They were only known up to 7 here. And so my good colleague Bartłomiej Pawelski from Poland actually found 2 of these in 2 separate papers, which was quite the advance. And he's done a lot of other really interesting work in the field as well. So yeah. The important R number here, or equivalence class count for our problem, is this one, the 7th one, because we will be doing all of our work in 7 dimensions. And so this 490 million kind of determines the amount of work we have to do. We've now come to the formula that I actually used in my work, which is the twojump formula. So this one was actually originally developed by my promoter, Patrick de Causmaeker. And it uses these so-called p-coefficients here in the middle. So we have a similar structure to before. Instead of iterating over 1 Boolean function, we now iterate over 2 Boolean functions in dimension n. And we multiply the interval size from the bottom of alpha by the interval size of beta to the top times this p-coefficient. And these p-coefficients are really quite important to speed up the computation. Now, we want to compute the 9th Dedekind number. So we'll need a data set of all of these interval sizes beforehand that we can use. And so this was also not present when I started my thesis. And this was actually, I would say, the primary accomplishment of my thesis at that time, was being the first ever to compute all of these intervals for the size 7. And so here you can kind of see all of my different attempts. Oh, we have a meeting in 10 minutes, Plessel. So, right. So these are the different methods that I explored. So here the green curve is the naive method. So basically the y-axis is time it takes to do a certain layer. So we start at the bottom layer, work our way up. And you can see it just, it's gone. It's like in the hundreds or tens of thousands of seconds, this was not going to finish. Patrick developed a different method, the interval size fast method, which did slightly better, but again, shoots up, it's gone, impossible. I then developed an incremental method where we basically always build up intervals from smaller intervals, and that one did even slightly better, but still it shoots up. And then finally, this is extensively documented in my thesis. I was able to do an optimization I call the powers of 2 optimization, where we can add up powers of 2 instead of just individual items to the intervals. And then finally, we made it across the big bell curve, and then a few more optimizations, and running it out on a supercomputer, we finally got all of our intervals. So this was actually a really wholesome moment with my family. Like, we would have the computer, my dad's computer on the kitchen counter, and we would set it going, and we'd go to bed and like come back the following morning and look, oh yeah, it's made it to layer 67 already. And yeah, this was this. And my mom would like add these to a spreadsheet. It was really cute. That was all during my master's thesis. So we have now a data set of all of these intervals. We have a data set of all of our monotone Boolean functions. So now we can finally attack the p-coefficient formula itself. And first, we want to apply a few more optimizations. So this is why I call this the expanded p-coefficient formula. So we've basically separated out the iteration for our alpha and our beta. And this way we can again make use of our equivalence classes. So here we iterate over all Boolean functions. Here we just iterate over the equivalence classes, which is about a factor 5,000 less. Sorry. For each element then, we can undo this, that we only iterate a part of them by just multiplying by the equivalence class size. For beta, sadly, we can't entirely do it the same way, because these p-coefficients here, they're dependent on both alpha and beta. And so they would be the same if we just limit our alphas to equivalence classes. But if we do it for both alpha and beta, the permutations of beta do influence relative to alpha these p-coefficients, so that doesn't work. So we still have to do all p-coefficients. But we can get some of the expensive parts of our computation out of this innermost loop by splitting up across equivalence classes anyway. And what we just do is we iterate over all equivalence classes of beta, and then just iterate over every permutation of this beta. And so we're doing it anyway, but we're doing the equivalence class first and then the permutations, instead of getting the equivalence class for every permutation. Why do we do it for every permutation and not for every element in the equivalence class? Because these equivalence classes, when you go really big, they basically all have the size n factorial. And so it's easier to just fix the code for a certain size, and this really helps in the later part for the hardware design as well. And we will get a few duplicates. We will get a few equivalence classes of size maybe n factorial over 2, or maybe n factorial over 6 or something. But it's a very small minority. Like 99% of all equivalence classes are size 5040. And so if we have duplicates, we can just divide them out by doing this fraction here. Like if we have n factorial over 2 equivalence classes, then this will just be 1 over 2. There was one final optimization I was able to apply to this formula, which I call deduplication. And that's basically, if you look at this big structure of monotone Boolean functions, it's symmetrical across the middle axis, and we can actually flip it around. And in fact, you can flip any Boolean function around and get an equivalent dual Boolean function, which, like if you have the red part on the bottom, you flip it over and you swap the colors, and you have an equivalent one, and we call that the dual. And in fact, if you run through the math, this equality here is true. Like, if we take the dual of our alpha, the dual of our beta, and then the p-coefficient of the duals, this becomes the exact same term. And so this way, we can actually halve the total amount of work we can do by just reusing the value we got for the first one here. Now, of course, we have to be careful that we don't count the instance where like alpha is equal to the dual of beta, double, so we have to filter those out. But still, we get pretty much a 50% speed up. And this 50% speed up was really, really important to get it feasible, because still, it was a very long project. Just to illustrate the total amount of work we have to do, we start for these alphas with 490 million equivalence classes in 7 variables. For every single one of these, we have to iterate over 45 million, this is with the deduplication, betas that may have a bottom below alpha. And then we have to iterate through all 5040 permutations for each of these betas. So the total amount of work we have to do is 5.6 times 10 to the 18th. This is an absolutely astronomical number. This is only a number that the biggest supercomputers can really reach in terms of computation speed. And just as a comparison, the number of grains of sand on Earth is about 7.5 times 10 to the 18th So we're pretty close to the number of grains of sand on Earth for the number of computations. I got that number from some website. I don't know if it's correct. So I don't know if the grains of sand should be more or if this is just a really, really big number. But it's a nice comparison. Now, this is quite the task. So we better figure out a way to compute these p-coefficients efficiently. And I will now explain what one of these p-coefficients is and how we compute them with the so-called Floatful algorithm. So basically, we start with a graph. And this graph is basically if you subtract all of the colored nodes from alpha from beta. So you know you had this Boolean function alpha. Let's say it was a bit of a bigger one. We have a permutation of beta that's below it. We remove all of the activated nodes from beta from alpha. Then we get this kind of intersection. Like some of the nodes here on the middle are left. And like all of these at the bottom, they were taken out by beta. And so the task here is, and why it's called this C alpha beta alpha gamma term, is we want to count the number of connected components in this graph. So in this case, I've colored them for you. So we have 1, 2, and 3. But how do we count this? Like, and how do you do it efficiently if you have to do it 10 to the 18th times? So a very naive algorithm we started with is the so-called Floatful algorithm. So we just grab a node. We can do that. Say this one. And from this one, we just explore all of the nodes that are connected to it. So we go to these, we go to these, we go to these. And now we can't explore any further. So what do? We remove this connected component from the graph, and we start again. We pick a new seed, we explore again, remove it, and repeat until the graph is empty. And so this method for this graph gives us a connected component count of 3. Now we can already apply some minor optimizations to this. This was still while we were working on the CPUs, but it applies to FPGAs as well, which is leaf elimination. So basically, we just start removing nodes beforehand so that our exploration step takes less time. But we have to be careful again. So the rule, like a leaf elimination rule we can do, is we can remove any node which is exactly one neighbor, because that should still leave the rest of the connected component intact. But the problem, of course, is if you have these annoying structures, which have exactly 2, these would eliminate each other. We can actually prevent this by only doing leaf elimination in one direction. So in this case, we have 2 variants, leaf elimination up and leaf elimination down, where we just say, OK, we'll just remove nodes that have exactly one neighbor below them and no neighbors above them. That would be leaf elimination up. And that is what is shown here. And in fact, for the practical algorithm, we don't actually need to do leaf elimination down at all, because just due to the way the iteration is structured, it would not have much effect. So just having the leaf elimination up already helps quite a lot. But we can actually go a bit further. We can do singleton elimination, which is basically we have now some nodes here in this graph which have no neighbors. And so our iteration also has to kind of visit these, remove them, or try and explore and then remove them, and then go to the next step. So it's always quite a lot of work. And we can also detect these and remove them immediately. And actually, there are quite a few singletons that remain after leaf elimination. So this helps quite a lot. And now we only have this one remaining block that we still have to do with our Floatful algorithm. So we've detected 2 singletons ahead of time. I've put it into a bit of code here. So it's pretty much what I explained already. So we take our graph in. So we remove the nodes from gamma from alpha. We do our leaf elimination. We do our singleton elimination. And then, while we can still remove nodes, or while we can still pick a new seed, pick a seed. This is explore up. This is explore down. And if we can still explore, we keep exploring. If we cannot explore anymore, if no new nodes are being detected, we stop, we remove our seed from the graph, add 1 to the count, and go back. And once we're done, we return the count. So this is the number of iterations it takes for this algorithm on CPU. So the gray curve here is the base, the baseline. So this is just floodfill, and it's very wide. Takes on average about 7 iterations. Only singleton elimination compresses this already a bit. And then if we have both singleton and leaf elimination, we compress the graph further, and we get an average runtime of 4 or 5 cycles, which is quite a lot better. And actually, singleton and leaf elimination both together make the hardware slightly easier to design as well, but we'll get to that right now. So these operations that we're doing, this exploration, this like these bit shifts, they're all binary. CPUs are not made for binary operations, strangely enough. Like CPUs are made for multiplies and complex control flow. And like the control flow in this algorithm is really annoying for CPUs. Like if you know a bit about computers, this while branch, it branches up maybe 50% of the time, branches down maybe 50% of the time. This one here also has maybe a 70-30% ratio. This is terrible for branch prediction. So CPUs are really bad at executing this code. And I've tried optimizing this for CPU, but it's not easy. But what it is really good for is hardware, because if we can just kind of make a chip that does this, because it's all binary, then we could have a far more efficient processor. And this is actually the reason why I came to Paderborn here, because they have one of the only FPGA supercomputers in the world. So for example here, I've shown you one of the binary operations that we use a lot. This is for the exploration step. So let's say we grab this node as our seed. If we want to explore all of the nodes below it, we can use this kind of fast Fourier-like structure to explore all of the nodes below it in a very short amount of steps. And so we have an equivalent one for exploring up and equivalent components for all of the other operations. And so now we get to the actual hardware designs. So this here is the very first instantiation of our count-connected core. I think I sent it in one of my earliest mails to you, Christian. Do you remember it? Yeah. But yeah. Like this is just the very basic structure of how we do it. So again, the same algorithm. A graph comes in. We store it in this register. We grab a random node from it, and we store it in the register that we're currently exploring. We do this monotonized up, exploring up. We do this monotonized down, we explore down. And we store it back in the current extending register. And we keep looping through here until there is no change. If there is no change, we remove our currently exploring area from the current graph. We store the new graph in our graph, and we pick a new seed. And we keep doing that until we're done. Now, of course, this is a really nice block to show, okay, the hardware works. We can implement it simply in hardware. But it's not going to run fast. And so this is where this diagram comes in. I spent a few days painstakingly drawing this. And this diagram has a very special structure, namely wires and signals always travel to the right. To the right, yes. And so here, this looping structure, I've made it kind of implicit, so the signals come out, and they go back in the registers on this side. And so here we can actually, again, see the structure that we had before. So here is our exploration pipeline. We do our monotonize up, monotonize down. We can check if the graph is empty. We can check if we are done with this current part of the exploration. We have a bunch of logic to handle inputs and outputs into this recurrent pipeline. And we have the logic that picks new seeds. And these are like the major components in this diagram. And why do I draw my diagram in this convoluted way? Well, There is only one reason, namely pipelining. If you have a design, a hardware design, the constraint to how fast you can run it is basically what is the longest path between two registers. What's the path with the most gates in between them? And so, like in this one, the path is all the way through here, through this equals, through the first bit thing, and then back to the register. This is a really long path, and we also had a similarly long path in the previous diagram. But we can just cut vertical lines through this diagram, and anywhere one of these lines cuts through a wire, we just put a register, and then everything is still in sync, and everything is still pipelined. And now we will actually have, in this case, 5 or 6 elements looping around in here, all being computed at the same time. But now, the longest length between two registers has become a lot shorter. Like here, maybe the longest length between two registers would be like this, and maybe it's about half the length from before. So we've about doubled our clock speed. And this is how you make performant hardware. In my case, I pipelined this hardware module 17 ways. So I've pipelined it into 17 stages. So at any given time, 17 different computations will be looping around in here. The problem is, this algorithm takes a variable number of iterations. So like if one comes in here and starts looping, and it has to loop maybe 10 times, and then the next one comes in and only has to loop 3 times, well, the one that has to loop 3 times will come out, and it'll be in front of it. So we need some way to reorder them, to put them back in order. And that is what this little structure here does. So basically, what we have here is, in here come our graphs, our input data. They are given an address. So this is an address counter. It counts up every clock cycle. And they're given an address, put in the FIFO. When this module is ready, it'll grab one element from the FIFO, start working on it, maybe spend 6, 7 iterations working on it, and then it'll write the output for this computation to that memory location in this output memory. And what this does is the next time this address counter, it goes all the way up, falls back down to 0 because of overflow, and counts back up, it'll read them all out in the proper order again from the output of the memory. And so this little loop block here puts everything back in order. It also has a very nice benefit, which is this green dashed line here, but I'll get back to that in a minute. But the one big drawback this module has is, what if we're too late? What if this module computes a certain element too late? Let's say an element takes 30 cycles to compute, or maybe 2,000 clock cycles to compute, and you only have 1,000 addresses here, then you'll have visited address 1,000 or whatever address it was given before it actually got written. And so then our hardware performs faulty. So we have to prove that if an element comes in here into the FIFO, it takes a fixed or a limited number of clock cycles before it actually gets written out, so that we're always on time and so that we never read stale data out of the output block. And so I had to find the worst case, which MBF, which graph structure here would take the longest time in this pipeline, and it's actually this one. And so what you see here is the middle 2 layers of a 7-dimensional hypercube. So you should imagine here above there's like a whole bunch of lines still going to the rest of the cube and below it. But the only 2 relevant layers are the middle ones, because they're the widest. And you can see why this is a really annoying example, because our exploration goes in steps of up and then down, and up and then down. And so this is just one really, really long chain. And so every node has exactly 2 neighbors, and so you'll start maybe, I think it was this node that had exactly 1 neighbor, and you'll go up and down, up, down, up, down, 1, 2, 3, 4, 5. And so this is a chain of 41 nodes long, so it'll take 21 cycles to fully cross the chain in the worst case, and this is the one we dimension for. So this is this is then the pipeline that we've actually implemented. So here our graph comes in. Yeah, ignore this for now. We'll get back to that. Our graphs comes in. We do our leaf elimination. We store it in the FIFO. We do our singleton elimination. Then it loops around in the count-connected core a bunch of times. And then we write it into the output memory. And we have our index counter here, which is producing the addresses. We do our power of 2, and we add them up. And that's like you will recognize the formula from before. Now I'll come back to this shaded region here, because we are doing high-performance computing. We want to do our computation as fast as possible. And so we want to make the part of our computation that's the most important, that's doing all of the computing, of course, the fastest. So this count-connected core, we want to make it really, really fast. We want a really good clock for that. But for everything else, like this leaf elimination or this permutation thing, like if one graph takes on average 4 cycles to process through here, then it'll take 4 cycles before this one has to produce 1. So we could actually make the yellow area a much slower clock. And this is really nice about this little loop construct we've got, because FIFOs and memory blocks are both really natural places to perform these clock domain crossings. And so in practice, we found that on the Intel FPGAs that we're using, there is actually a second faster clock that we can use for this one, which runs at about 450 megahertz. And then we leave the rest of the hardware around here at our base 225 megahertz. And so this way, we can optimize the part that really matters, and we don't need to spend too much hardware pipelining all of the other components. Now, let's put it on an FPGA. This is, I think, the very first FPGA synthesis I got for this project. So it's they look kind of like lungs for some reason. I think it looks pretty cool. And so you can recognize some of the structures from our hardware pipeline here. So these blocks here are the output memory. These blocks here are the input FIFOs. We have some computation going on here, more computation going on here. I think these are like the new seed and other pipelines, but they had different names before, so it doesn't match anymore. And also we've been able to compress it quite a lot. So for those of you who are unaware of what FPGAs look like, FPGAs are basically a giant grid of logic cells. And so the most common ones are these blue ones here. They are the normal computation cells. So these just contain lookup tables. Basically, they're just gates. You can say, okay, this one does an AND operation, this one does an OR operation, this one adds 2 numbers, like really small operations. Then these yellow ones are memory blocks, which is how you can recognize the input FIFO and the result collector. And on the FPGAs I use, they are M20K blocks, so 20 kilobit blocks. And then finally, we have these gray bars here in the middle. These are big multipliers, but I did not use them. Other people in my department use them quite a lot, but I had no use for them in this project. So now we've built a very basic hardware module. We can run it at a really high clock speed. And if we're doing supercomputing, then the next step is parallelize. And so one obvious place we could do this parallelization is at the level of these permutations. So we need to do our 5,000 permutations for this last term of the formula. And so I've divided them in this diagram here in a certain way. I call this a permutation diagram, or a permutation split diagram. So our betas come in over here. They get stored in the FIFO here. And we do our first 7 permutations. We can split it up across the factorial. So we do our first 7 here. We can check which of the permutations is actually valid, because not all will be valid. And then we parallelize. So the next 6 we just do in wires to 6 different branches. Each of these we can split in 5 again. And now we have 30 pipelines that can run in parallel and each of them does the last 24 remaining permutations themselves. So here, every time a block of 24 comes in, if at least one of them is valid, it gets stored in the FIFO. Each of them is then permuted, sent to the PCoefficient core, and we store all of the results in this FIFO. When all of the cores have a result for a particular beta, or a summed result for a particular beta, we will add them up and send them to the FIFO for further collection. So, nice parallel block. Let's put it on an FPGA. And now, this is a weird-looking spider thing, but you can again recognize the parts of our hardware. Like here in the center is kind of some management logic, and all of these little blobs here are our individual PCoefficient cores, like we call them. And so these are like the 30 little blobs that surround it. And if you mark it on the FPGA, you will actually see them. But as you can see, there's still quite a bit of free space on our FPGA. So let's parallelize. Let's go for 2. Let's go for 6. And now the full FPGA finally comes into view. Maybe 10? Nope. The compiler could not handle this. It was mixing them up, drawing long wires all the way from across the FPGA fabric. Timing was failing left and right. Did not work. So we also got terrible performance. I think even the maximum clock speed that we could get, if it worked, was like maybe 80 megahertz or something. Terrible clock speed. And so we were kind of bummed at the time, like, how do we fix this? And there is this concept in FPGAs called logic lock regions. So I was able to test that if I just like push one of these blobs all the way into a corner, it still gives really good hardware. Like it still runs at 5-ish 100 megahertz. So we can do that for all of them. And Intel certainly did not make this easy. Like they did not expose this anywhere. Documentation was nowhere to be seen. I had to kind of figure it out. I actually edited the board support package for these FPGAs here to get my timing constraints and these logic lock region constraints in. And that was mostly thanks to the help of Tobias and Michael, I believe. So big thanks for that. But doing this, we finally tamed the compiler slightly, and we got our solid performance. So we got a nice 450 megahertz, 92% logic density within our own part of the FPGA. We could not touch the bits of the FPGA that OpenCL was using rather inefficiently, sadly. But still, the area we could use, we did use. And so we got a total peak performance from this of 300 million bottoms per second. This is an astronomical number, like because each of these is 5,040 permutations. So we're getting a very, very powerful chip here. Now, we have a chip that can process data very fast, but we actually need to get the data into the chip as well. We need to get these graphs and these alpha and gamma MBFs in there. And so at this point, our chip was really fast, but the PCIe bus connecting the FPGA to the rest of the computer was not. So we have to compress our data that we send to the FPGA. And we do that by storing a lookup table on the FPGA's RAM itself. That's this one up here. And this one contains the full 128-bit wide MBFs. And then we just send over an index buffer. So the first one is special. It is the alpha that we send over. And then all of the other ones are the betas that are like supposed to be combined with it. And so this way we can actually send all of our MBFs efficiently enough that we end up slightly below the maximum bandwidth of our PCIe interface. Our output sums are about 48 bits wide. And yeah, because we were using OpenCL for our interface, we had to use 64 bits. So I guess we stored some extra information in here, just the number of permutations which were valid. And in the end, it turned out that keeping this extra information was really, really useful, because it actually helped us correct any errors that were still in the count, in the solution. Finally, we have a few more bits, and we just stored some ECC flags in this. So this means all of the memory blocks we use. Sometimes the FPGA gets hit by cosmic radiation, and that may flip a bit in a memory block usually. And so they all have built-in error correction. And to get this data out, we use this ECC bit here. But throughout our entire 3-4 month run, we did not see a single ECC error. So I guess the numbers predicted that we should get about 0.3 over the whole run. So like a bit more than we'd like, but not so many that we wouldn't get any. So we got 0. I guess it just happens. Now let's do a performance comparison of this FPGA monstrosity versus what we have here at Noctua 2. So our servers here, they have servers with 2 AMD EPYC CPUs, each of them 64 cores. If we parallelize over all 64 cores of one CPU, we get a crushing 0.6 million bottoms per second. On our FPGA, which has 300 PCoefficient cores, we get 300 million bottoms per second. So we have a speed up or a speed advantage of a single FPGA versus a single EPYC CPU of a factor of 500, which is astronomical. Like, it's one of the largest FPGA advantages, I think, in our department. Now, we finally got this device that can compute these values really, really efficiently. Let's do some supercomputing. We have more of them. Let's use them all. So we generate these beta buffers. Like we finished this. We generate our beta buffers. I'll just go over this quite quickly. Basically, this is a diagram showing for every alpha of a certain size about what fraction of the betas of a certain size are actually below it. And so you can see if we cut off a lot of, like, if we can follow this curve nicely, we actually can cut off quite a lot of unnecessary work. And that was also part of my thesis. So I figured out this method of finding exactly the equivalence classes that lie below another equivalence class. But this is not really core to the ID, but the algorithm looked something like this. So you start at your hypergraph for your equivalence class, and then the structure here is basically every connection you follow up, you add an edge between the nodes that we had already. And so you can start at your node, or you can start at your MBF and go all the way down, and this way you can find them really efficiently. For our supercomputer that we have, each of the nodes have 2 of these 520N bitware FPGA cards, and also 2 really beefy CPUs here. So we want to put them to good use, and this is the threading diagram for our process. So we used 16 threads here to generate these big beta buffers. We then had our 2 FPGAs, which both get this lookup table for our monotone Boolean functions. When they finish, they store their results in this queue, and they are grabbed out by 8 threads that do result aggregation. So they just add up all of the results that the FPGAs produce, multiply them by the proper interval sizes, and we ran it such a way that we reused all of our memory. So each of these buffers is in a closed cycle, and they get recycled every time we use them. This all takes quite a lot of memory, so we're about at the limit of these Noctua 2 nodes. So we have 512 gigabytes of available memory. We needed to have 2 copies of each of these buffers in RAM for NUMA purposes, for more efficient access to them. And we needed all of these buffers. So in total, we are really hitting that 512 gigabyte limit. And this is also why we need to do our buffer recycling, because we really don't want to run out of memory. We want to just run a fixed amount of memory all the time. So we can now process buffers of beta really quickly. What do we get for all of this work? We get, for a full supercomputing server, 2 of these beefy FPGA accelerators. We can do 5.8 of these alphas every second. And we need to do 490 million. And at this point, it becomes real supercomputer and just a game of waiting. So we divide the whole thing up into 15,000 jobs. We allocate about 333,000 TOPS per job. Each job took about a little under 2 hours, and we had 16 FPGA servers. So after 4 months on Noctua 2 and 47,000 FPGA hours later, on March 8th at 5 p.m., I finally saw this number come out on my terminal. But we weren't there yet, because we had this issue on the cluster. Namely, every so often, the communication library for talking to these FPGAs would just forget to copy a tiny amount of memory. And so maybe every 2 or 3,000 buffers, or even less, every 20 or 30,000 of these buffers, we would just get like one tiny error in this massive buffer. And so we did not, we tried to solve it at the time, but we could not detect these errors. And so we kind of just had to deal with them. At this time, it's also been fixed. So Michaelas also published a fix for that on the cluster itself. Though I don't know about any other clusters who might also have the same issue. But we still had to deal with it, because the fix came in when we had about 200 jobs left. So at that point, wasn't much reason to implement it anymore. But luckily, very luckily, we kept track of this little term here. And this term is really easy, or reasonably easy, to compute on CPU. And so after having processed all of our jobs, we put in a smaller supercomputing project, which was just CPU computation, to check all of these counts. And we found, I think, about 1,000 more buffers which had a mistake in them. And so we removed all of those, and finally we had our results. All of that was done on Noctua 2, here at Paderborn. I thank you for your attention. Are there any questions?
Would you do it again?
Would I do it again?
Yeah, if you knew it would take 3 years of your life. So what do you have to learn, and would you do it again?
Well, I think doing it a second time would not take 3 years. Well, I'm here, aren't I? So yes, I would. It was a really nice adventure. I came into contact with a really interesting university and a department where I'm doing what I want to be doing in life. So I would recommend it to anyone. So go compute the 10th one. You still have a chance.